all over the world, there is a constant search for better ways of moving materials. Efficient materials handling depends upon the selection of the best method for the case in hand. It may be novel or it may be well tried. What matters is that it is appropriate. Whatever the nature or scale of the operation, whether a material is handled loose or packaged, due consideration must be given to all the factors involved: material characteristics, often the circumstances of the site, or considerations of storage, processing, and distribution. We are concerned here with some ways of handling granular or powdery materials in the loose state. Let's look first at some examples of mechanical methods. This is a totally enclosed circuit conveyor at the British Oil and Cake Mills, Avonmouth, carrying material to a number of discharge points and recirculating material not drawn off. The hopper feeds reserve material to the conveyor by gravity as required. The conveyor moves on fully charged. With the cover plate removed, material can be seen conveyed en masse, with little movement between the particles. There is no danger of choking, as once a given level is reached, no more material can enter the conveyor. The key to the en masse movement is the use of U-type flights. These are suspended from one side only, the form of suspension and drive allowing the conveyor to make a tight half-circle turn. Machines of this type can be designed to convey in any plane without the need for a separate power source at major deviations. The material is conveyed with a steady, gentle movement, its quality unimpaired. The material discharges into process. The rate of draw-off in this case controlled by a rotary feeder at each point of discharge. In normal operation, the conveyor is totally enclosed and dust-free. Fire and explosion risks are thus minimized. Conveyors of this type can feed dry or damp materials at relatively high temperatures to many points simultaneously, carrying from a few pounds to many tons of material per hour. Another handling problem arises at Wall's London meat factory, where the composition of one of the materials must not be disturbed before processing. These rusks, used in the manufacture of meat products, are of more than one particle size. The rusks arrive in sacks, as if transported loose in bulk, the different particle sizes would separate. It is practicable, however, and more economical, to move the material loose once in the factory. At this point, the rusks pass through a hopper, particle segregation being within acceptable limits. Movement from cutting and tipping into weighing is by simple bucket elevator. By slowing the movement, the material can be seen carried to the process hopper without undue particle separation, the rusks normally being conveyed to process totally enclosed and uncontaminated. The most appropriate technique for a given case is not necessarily the most modern. Old and well-tried methods can often provide convenient and economical answers to many problems of materials handling. Here, however, demonstrated by the manufacturers, is a more modern piece of equipment, with safety guards removed for clarity, capable of dealing with the same kind of handling problem, the zipper closed belt conveyor. This machine can handle a wide range of granular, flaky, or lumpy materials, but is not suitable for sticky ones, nor should it be used with material above 50 degrees centigrade. The zipper will convey its load en masse. In slow motion, the method of enclosure is clearly seen. Here is a conveyor elevator capable of working in any plane. It can operate at various speeds and requires only one power source, irrespective of deviations in plane. The material flows in a placid column, enclosed and totally dust-free during conveying until the zipper finally discharges its load cleanly and completely. But loose materials are not always best handled by single items of equipment used in the accepted way. The barge, developed by local management at BOCM Avonmouth, self-discharging, though not self-propelled, shows how a comprehensive system using conventional units of equipment in combination may result in a novel and highly efficient technique. The barge carries barley, milo or maize and can be used for other similar materials. No single piece of equipment in the system of discharge is novel, but the combination of component parts makes the device of special interest. Basically, the equipment consists of 2 conveyor elevators and 2 Sinden throwers. The thrower chutes are quickly connected to the 2 head boxes. Power is supplied from the quayside, the electrical loading for maximum discharge rate being 40 kilowatts. Now, without removing the storm covers, the entire load will be discharged in less than 3 hours, completely dry, in any kind of weather. Here, for demonstration purposes, the storm covers have been removed, and the thrower chutes, which would normally feed the shore conveyor, swung back over the barge to show the rate of unloading. Both chutes operate simultaneously, and working to full capacity, the discharge rate can reach 100 tons an hour. When unloading, the grain falls to drag-link conveyors in the bottom of the barge, the conveyors carrying the material to the 2 Sinden throwers fore and aft. Without trimming or other manual aid, the material is withdrawn in such a way that the barge remains throughout on an even keel. The increased rate of discharge and complete weather protection has greatly reduced turnaround time, allowing more trips per week. On a short-haul operation, this more than compensates for space given up to hoppering and results in considerable savings on the methods previously used. The shore conveyor carries the material to storage, dry and ready for process, its quality maintained. No 2 materials handling problems are ever quite the same. The answer may lie in a search for new ideas, or it may be in well-tried and proved techniques. The challenge is the selection or adaptation of what is most appropriate, and the reward is better flow, better working conditions, and the reduction of handling costs. A difference in air pressure between 2 points in a system can cause a flow of air towards the region of lower pressure. This flow can be harnessed, where appropriate, to transport materials economically and swiftly from storage to process. The use of air to assist the movement of materials is called pneumatic handling, and it is the application of techniques using greater than atmospheric pressure for the movement of suitable dry solids with which we are concerned. These systems offer advantages when material characteristics and site conditions are appropriate. Let us consider first some important characteristics. Angle of repose is one of the first considerations affecting both handling method and equipment design. Some materials create problems in handling due to their abrasive nature. Silica is a typical example, but handled pneumatically, the problem largely disappears. Particle size and shape can affect the choice of equipment. Some materials, such as stearine, can be supplied in different forms, and in bead form, it is well suited to pneumatic handling. Hygroscopic materials tend to cake, For example, salt, which also becomes corrosive when damp. Vacuum-dried salt, however, is free-flowing and very suitable for bulk storage and pneumatic conveying. The way in which materials with the right characteristics can be handled in a pressure system can be shown by the use of a model. Here is a powder transfer pump designed for the movement of suitable materials by compressed air. The pump is made airtight by closing the powder inlet cap. Air is then applied above the powder to pressurize the vessel. When the operating pressure is reached, compressed air is admitted to the powder discharge line. The discharge valve is opened, allowing the powder to drop into the high-velocity airstream, and the powder is then conveyed along the discharge line. The powder maintains its flow through any deviations in plane. The material can be moved over considerable distances and to levels far above the pump itself. The transfer of material normally continues without further attention until the compressor is switched off. The practical application of this type of pressure pump is shown at the British oil and cake mills, where salt, which was previously carried in bags, is now delivered from the suppliers in pressurized vehicles. The air required for transfer can be supplied by the vehicle or obtained from a compressor in the factory, pressures varying according to the material and the height and distance it is to be conveyed. The whole operation is controlled by the vehicle driver alone. Discharge to the silo being effected at the rate of 20 tons an hour. During delivery, the silos are vented to atmosphere through dust collectors to avoid any nuisance. The use of dried salt has eased weighing for process, and the new system has released much-needed floor space, freeing staff once engaged in arduous bag handling for other and more congenial work. Incidentally, as a further small plus, the changeover has produced an overall saving of 25%. But the pressure pump is only the start. Another way of handling suitable material pneumatically can be demonstrated by a model using air to change the natural angle of repose of a powder. The powder is supported on a porous bed through which air is passed up into the material, reducing friction between the particles and causing it to behave like a fluid. This technique is called fluidisation. The model shows how a powder can be made to flow, where a slight incline allows gravity to assist. Moving a material by this method is known as fluidized conveying. A fluidizing conveyor is of simple construction, though careful design is essential if it is to be efficient. It consists of an upper section in which the powder is contained, resting on a bed, made up of lengths of suitable porous material. This can be fabric, sintered metal, or, as in this case, porous tile. Air is fed from a lower box section to the porous bed and so into the powder. When air is applied, the powder behaves virtually as a fluid. In fact, if you haven't got a pond handy, you can float a boat on it. This fluid state continues as long as air passes through the material. By clearing the powder to one end, it can be shown how a fluidized material can be conveyed by gravity wherever a downward incline is maintained. Only a gentle slope is required, the degree of incline depending on the material to be handled. A fluidizing conveyor is seen in practice at the factory, moving phosphate from a silo to a powder transfer pump. With the cover plate removed, the fluidized powder is visible, its angle of repose greatly reduced, flowing swiftly down the slight incline, the flow starting and stopping as air is switched on and off. Large quantities can be conveyed with very small power consumption. A large volume of low-pressure air is the requirement. This blower operating at only 20 inches water gauge. The use of fluidisation in storage can be demonstrated by returning to the glass model now adapted to represent a fluidising gravity silo. The vessel is open to the atmosphere, the principle of operation being similar to the fluidising conveyor. The powder outlet pipe here passes through the airbox in the bottom of the vessel, the top of the airbox consisting of a porous plate. When the vessel is filled, the powder rests on the plate. When air is passed up through the porous medium, the powder is fluidized. If the air velocity is too high, the powder behaves like a boiling liquid. Only an adequate supply of air at the appropriate pressure is needed to keep the powder in a fluid state. Once the discharge valve is opened, the powder flows out by gravity. The fluidized material moves freely and easily so long as the air supply is maintained. When the air is cut off, the material once more compacts. When air is turned on, the flow recommences. This is the system used at Port Sunlight for the storage of phosphates. The silos are fitted with air boxes similar to that of the model, and their operation is the same as in the demonstration. When the air valves are opened, the phosphate is fluidized. The powder delivery valve is then opened, and the silo begins to discharge. The base of a fluidizing silo can be made almost flat, giving better space utilization. The silos can also store to a height not possible with bagged material, and the material may be fluidized periodically to prevent compacting. Let us now return to the model powder transfer pump, modified to allow fluidization. The pump is closed to atmosphere. The lower part of the model embodies an airbox, but now the powder discharge pipe is set above the porous plate and passes out through the top of the pump. When the vessel is filled, the discharge pipe is submerged in powder. Air is passed up from the airbox through the porous plate to fluidize the powder and pressurize the vessel. When the operating pressure is reached, the discharge valve is opened, allowing the fluidized powder to be blown from the vessel. Air is bled off from above the powder level as necessary to help the discharge by diluting the air-powder mixture. With fluidization, the powder transfer pump is enabled to handle a wider range of powders while offering the same advantages as before. Here, a fluidizing powder transfer pump is used for the movement of silica powder at Port Sunlight. The pump is 300 yards from the process plant, the powder being blown through a pipeline to a height of 85 feet. The rate of discharge is 40 tons an hour, and as with the demonstration, the whole operation is controlled by one man. The compressor, driven by a 60-horsepower motor, delivers 320 cubic feet of free air per minute at a pressure of 40 pounds per square inch. The operation is dust-free and wear on the equipment negligible, resulting in a saving of over £10,000 per annum on maintenance alone. Pumps are made in many sizes, from 100 weight to 100 tons capacity, the larger pumps also acting as storage silos. These pneumatic techniques are well suited to automated or remote control operation. A good example of remote control can be seen at the Belgische Margarine-Unie Merksen, where a transfer pump weighing unit is fed with bleaching earth from 2 fluidising storage silos. The pressure vessel takes the place of a scale pan. The whole operation, drawing off, weighing and blowing to neutralizers, is controlled from a panel at the refinery about 100 meters away. By remote control, the batch weight of the pump can be preset from 0 to 200 kilograms. The powder can be discharged by a center point system into any one of 5 neutralizers. The procedure is simple. Air is applied and the fluidized powder fed from the silos to the transfer pump. When the batch weight is reached, the powder supply valve closes automatically and the earth is blown to the refinery. Controlled throughout by one man, the transfer of materials from storage to process is simple, clean and efficient. The value of these methods in increasing productivity and improving working conditions is well illustrated at Lever Gibbs in Milan, where we can follow the flow of materials from delivery in transfer pumps through storage silos and day bins to process, all movement of materials being by pneumatic techniques. Delivery of 3 basic materials for NSD powder production is made by fluidizing transfer pumps of the type previously demonstrated, an arrangement negotiated by Lever Gibbs with the suppliers. Each pump on the vehicle is separate, so that more than one material can be delivered and discharged on the same trip. Air for the pumps being supplied by the factory compressor. When material is required, it is fed by fluidizing conveyors from the silos into the powder transfer pumps below. The material is conveyed along some 120 meters of pipeline and then up to a height of about 15 meters for delivery to the day bins. There is one day bin for each of the 3 materials, extractor fans being switched on automatically to vent the bins during filling. Then from the day bins, the 3 materials are fed by fluidizing conveyors to the weighing unit, which is situated below. A point of interest is that each fluidizing conveyor is fitted with a pneumatically operated cut-off valve. This keeps the batch weight error within 1%, as the valve stops the flow of residual powder in the conveyor directly the batch weight has been reached. One weigher deals with 3 materials, separate needles on the scale being preset to give the desired batch weight for each powder. Indicator lights on a control panel show which material is flowing. As the operator at the control panel calls up a given material into the weigh scale, a series of operations is started off. The correct air feed pipe on the multi-weigh valve is automatically selected. At the same time, the cut-off plate valve in the fluidizing conveyor is opened, allowing material to flow into the weigh scale. Air for all 3 conveyors is drawn from a single blower. When the weigh scale records the correct weight, the cut-off plate valve closes automatically. The powder discharge valve below the weigh scale then opens to allow the material to fall into the slurry pots below. The raw materials are fed into one of the pots and thence to the remainder of the process. What was once a very dusty factory is now an exceptionally clean one, and as a consequence, working conditions have improved beyond recognition. Furthermore, production had previously been seriously handicapped. The restricted site, completely enclosed by residential property, had made it impossible to hold adequate stocks of raw materials in the factory, resulting in additional costs for outside storage as well as extra handling. Pneumatic systems have overcome these serious difficulties, bringing reduction in handling costs, better factory layout, cleaner working conditions, and substantial improvement in health and safety factors. Here is the clearest indication of the benefits that can come from the imaginative use of pneumatic techniques. So flexible are these techniques of pneumatic handling that there seems almost no end to their application everywhere, from the factory areas to the transport of loose materials from the supplier. This road vehicle, for example, is a 3-compartment fluidising pressure pump. On rail, the British Railways twin powder pump wagon with a capacity of over 570 cubic feet has been specially designed for transport of loose materials in bulk, yet another essential link. And on the River Rhine at Mannheim is a barge carrying 400 tons of silica in 20 pressure vessels for the Sonnlichtgesellschaft. This barge, with a crew of 3, moving only by daylight, gives an economic operation on a round trip once a week of over 300 kilometers. The advantages of this system are emphasized when the Rhine freezes over in winter, to provide for which advanced supplies must be brought in and stored in bags, a costly procedure. Here again, with the adoption of an appropriate pneumatic system, the whole discharging operation has been simplified, resulting in substantial savings and the elimination of much arduous work, while the health hazards so often connected with the handling of silica have disappeared. Once connected with the shore, the barge discharges the silica powder at the rate of 40 tons per hour, an underground pipeline providing a convenient means of crossing third-party land to the factory silos 150 meters distant. The silos, each of 100 tons capacity, are fluidized pressure pumps blowing the silica directly to the day bins without recourse to ancillary transfer pumps. By water, rail and road, the versatility of pneumatic techniques is making it possible to move suitable materials without manual handling through all stages of transport, from supplier right through to process. Here, fuller's earth leaves the supplier for a 250-mile journey by road and rail to the factory. The ease and efficiency with which material can be transferred from one type of transport to another allows full advantage to be obtained from favorable freight rates. The cost of double handling after a short trip of only a mile from supplier to railhead has been reduced, and this has now become an economic proposition. The material will not be handled manually at any stage of the journey. Transferred pneumatically from one vehicle to another and eventually to the storage silo, even in the worst weather, the quality of the material is not impaired. At the factory, simplicity of operation and complete cleanliness of handling are achieved. Once transferred from the delivery vehicle to the silo, the material can be conveyed and routed anywhere a pipeline can be run, illustrating once more the possibilities of throughout movement by any form of transport, straight from the supplier without manual handling into process. Every materials handling problem has to be considered in relation to the sum total of local circumstances. But the aim is constant, to reduce costs and conserve skilled labor, to widen margins of health and safety, to make better use of space, and to improve the flow and quality of production. Used either in proper combination or in conjunction with mechanical techniques, pneumatic handling systems in industry have a growing contribution to make.